Hello, everyone. Welcome. Today is Tuesday, March 25th, 2025. This is Transformative Vertical Flight Working Group on Public Services, meeting number 96. Welcome, everyone. Today we have a special invited speaker. Randall is the founder and CEO of Maglev Aero, Inc. He's going to talk about the Maglev electric propulsion. It's, from time to time or once in a while, we run into some really out of the box innovation. And today's topic is, to me, one of those. Now, before we start getting to the main topic, let me give you guys a few reminder of some of the meetings coming up. One is the H2 Aero, organized by Vertical Flight Society, on April 2nd to 3rd in Long Beach, California. Will be very interesting, informative. The other one is the Sun and Fun. It's going to be in Florida, Lakeland, Florida, April 1st to 6th, 2025. To my understanding, there will be at least a couple, maybe more, like eVTOL going to be there. Pivotal and Lift are planning to be there, and perhaps more. So it will be interesting if we can see you guys there. And on the right-hand side, there is the FDIC International meeting, April 7th to 12th. It represents the Fire Department Instructors Conference. Has a lot to do with what we talk about in many of our meetings and discussions and papers and so on. Next will be probably the AUVSI exponential meeting. This year is going to be May 19th to 22nd in Houston, Texas. I do plan to be there. Actually, to me, that's a very important, interesting meeting because many of the some of the underlying technology enable our eVTOL development. Actually, some of them came from the industrial or government use heavy drone industries. There's also SAE Aerotech. It's going to be in Vancouver this year. That could be fun in early May. And one important one is the Forum 81. It's going to be in. It's going to be a very large scale meeting. It's going to be in Virginia Beach, May 20th, 22nd. So hopefully, hope to see some of you in some of those meetings. And let me get back to introduce what the our speaker Ian is going to talk about. Well, first thing first, Maglev Aero is an innovative startup building a groundbreaking electric VTOL platform, the foundation for a range of high-performance, ultra-quiet vertical flight system for urban air mobility. Ian will present Maglev Aero's vision for the future of ultra-efficient, high-speed flight, leveraging Maglev propulsion paired with hydrogen power and so on. I'll tell you what, it's best for Ian to explain all those magical stuff to us. So I'm going to hand the floor to Ian. Ian?
Guys, thank you so much for the opportunity. Johnny, thank you for inviting me. Andy as well. Much appreciated, guys. I love this community and just the outstanding insights that you guys deliver, raising the level for everyone involved. Let me see if I can share my screen here to screen 3 here. Share. And the date is wrong, but the content should be up to date. Let me know if you guys have visual. Outstanding. Very good. I got a thumb. Thank you. Okay. So my name is Ian Randall. I'm co-founder and CEO of a company called Maglev Aero. We build maglev electric propulsion products for vertical takeoff and landing and high-speed cruise applications such as eVTOL or hybrid VTOL vehicle systems. My background is aerospace engineering with double E from Purdue University. Worked on a few things from land speed electric motorcycles to suborbital payloads, and did a lot in my early career with VTOL, where a lot of the early challenges that I had were in the power systems, like the batteries were rated for so much thrust or rated for so much power density, but delivered less than that. And then the ducted fan systems that we're using for this high-speed tilt duct, aircraft were delivering less thrust per unit power as well as, and so it was a hard place to be. And then after solving those, power, which ended up being weight challenges, at our flight demonstration, the most remarkable thing about our demonstrations was how deafeningly loud it was. So I ended up focusing on propulsion afterwards, and came to a certain set of conclusions where the losses were coming from, where the power was going, and where the noise was being generated, which led me down the route of Maglev Aero now several years later. So let me see. I'm going to give you guys a bit of an overview of Maglev Aero, our core value proposition, so you understand, what we do, why we go sufficiently far out of our way to try to do it, and what it means in a example use case that I'm particularly excited about, which is VTOL blended wing body vehicles leveraging hybrid hydrogen powertrains. And then, of course, this is one of my most favorite kinds of groups to be able to present to. So I'd love to, discuss and have good questions and comments at the end if possible. So I don't know if I'm going to consume the full time here, but I'll try to be efficient and elaborate with describing what we got. So brief history, worked on a few projects, ended up spinning out from a competition called Design. It was the Boeing Go Fly competition, where the objective was to design, build, fly, test a small under 8-foot VTOL system and fly it in a course. We ended up pulling out of that competition, spinning out the core technology, starting Maglev Aero from that, and worked on the core technology validation, raised a seed from Breakthrough Energy Ventures Material Impact, filed the core IP, and since then have been busy. We've gotten all of our patents, done a few partnerships, performed a subcontract under DARPA on the Sprint program, and then also developed a demonstrator of the core initial technology platform, which was a maglev rim-driven prop fan with individual blade pitch control, and learned a lot about these maglev motor systems, the losses of an open fan system, and have developed is our launch product, which is these tip-driven systems for high thrust capacity. So at the overall level, think of us as a maglev motor fan integrated system with a few different embodiments. There's on the right, the hub-driven system that's seen on our website with that tilt rotor, tilt fan in wing around the body system. There are also these tip-driven shrouded fans that leverage a magnetic bearing motor system at the rim of the fan. I don't know if you guys can see my mouse, but at the rim of the fan, that is the similar application with pretty outstanding sets of benefits, and then high-speed applications that we anticipate will follow shortly after. The overall net objective is really efficiency. Improving your efficiency has a pretty outsized effect on the overall vehicle performance capabilities. And so that's what we prioritize with these vehicles. And we make sure that we don't do that for higher costs and weight as well. But if you can reduce the power required for VTOL and or cruise operations, then you open up a lot more space on the vehicle for either payload or fuel capacity for range or endurance, and that tends to matter. So this presentation is going to focus on the tip-driven applications, and this is our tip-driven maglev fan system. We call it the TX series. But high level, we take technologies more commonly employed in high-speed linear maglev, and we wrap it in on itself. And we had good fun making this and this visualization, because essentially that's what we're doing. It's a big linear motor turned into a rotating motor, which at the end of the day for electromechanics, they're the same thing. This has those two embodiments, the hub-driven fans as well as the tip-driven fans. So instead of the blades sticking out, the blades are sticking in, and that has some pretty outstanding benefits where we can load and power these things with less losses and higher power density. And so it has two different kinds of embodiments. There are used for vertical lift for fan and wing, fan and duct, fan and tail, fan and body, shrouded fans, where you install multiple or a single, of them in the body of your vehicle for high thrust and high bandwidth kinds of applications where you want these fans in a lift plus cruise kind of configuration. We also find that the torque and speed of that fan, while good for high disk load hover applications, is also quite well matched for fairly high speed applications as well, high speed ducted fan applications as well. And so these are two areas that we focus on. And I'm going to be talking to you about the vertical lift applications, because this is the Vertical Flight Society. This is where we make things go up. The reason why we go sufficiently far out of our way with maglev is because rim-driven things are actually fairly complicated. That's why we don't see too many of them. So rim drive is, you imagine, a big motor, big diameter, very large moment arm. You get a lot of torque per unit mass involved in that system. This is all great stuff. The challenge is that oftentimes when you add a large motor out at a fairly large diameter, it adds a lot of destabilizing forces. Think about it this way. If you were to take a magnet, which I usually have one on my table. Okay, so I'm going to instead use my pen. Actually, here. If you're going to take a magnet, which is this phone, and your steel for your stator, and it gets closer, it wants to be closer at a much faster rate, basically with the inverse square of that distance. And so if you think about a very, very, very large diameter motor system, as the rotor has small deflections just due to the unsteady loading, the imbalance of aerodynamic forces, the inertial loads, the imbalance of the inertial loads, whatever the case may be, as those structures deform where nothing is rigid in these high-speed applications. And as they get a little bit closer, you can create fairly large, attractive destabilizing forces just from the electromagnetics of a large motor system. So this is usually why we don't see very large rim-driven motors, because to be able to enable that large torque density, you need to have a lot of structure in the stator vanes holding your bearings, a lot of structure in the blades being able to resist those deformations, things keeping that air gap very small, but also consistent throughout the operation. And so ultimately, you'd either have to put a very large diameter, high-speed rolling bearing out by those blades, or you need heavy structures. The result is it's heavy, and you'd also have lower lifespan, and you'd be, replacing components like Formula One transmission sets here, and it's a challenge. So what we do is we have a maglev motor technology that effectively floats the rotor so that it does not add destabilizing effects into this net system. And then we throw some maglev sprinkle onto it where we can also augment the stability of that with additional stiffness or damping, whatever the case may need. And it's good for high disk load thrust applications and high cruise speed applications. We find if for really low disk load, you're going to be better off with an open fan and a small torquey motor. This is a quick video of our test rig where we kind of pulled everything together. It is I guess the first maglev motored prop rotor with individual blade pitch control. I don't know if it was a milestone that many people were fighting hand over, feet to try to get to, but we were the first to do it, which is always fun to be able to say. In this video, you'll see individual pitch control where we have a servo actuator at the root of every blade. That was important for that large diameter hub-driven system where it has 2 sets of coax rotors. And our maglev motor bearing system all working in unison to be able to produce our target levels of thrust at our target power levels and make sure that the tool sets that we developed often from scratch to do the maglev aero mechanics, basically how does everything shake out and integrate with the aeromechanics and the electromagnetics, make sure all of those things are all accurate. So that rotor system is hollow, but inside of it is a large set of measurement devices, a very flexible circuit where we can configure it for either active or passive control or passive dynamics, a 6 degree of freedom, force transducer, vibrometers, many temperature sensors, many laser distance measurement devices, many other different state estimation devices, and has been a rig of ours that we use to validate the tool sets that we use to design these things. So what are we doing next? We're doing this tip drive next, and I have a prop next to me because props are fun. These tip-driven propulsion units we found address a critical need in some of the challenges associated with producing a fairly large amount of thrust in a fairly confined space and not suffering from a fairly egregious power required to be able to produce it. And so we have our maglev rim drive on the outer portion. We have internal bearings that help constrain certain motions of the rotor, but as you can imagine, that's a very long distance between the blade and the motor system, and so that over that distance you can have various deformations that either need to be mitigated or stabilized, or the effects of potential crashing events between your rotating elements and your stator elements need to be mitigated one way or another. And we have a series of inverters distributed around to help power the system. This allows us to have much better duct augmentation, much lower losses in the blades, and deliver the power with a higher power density overall. So the key thing that I'm going to get at actually is going to be the tip losses. If many folks in this community have worked on ducted fans, you probably remember the fairly severe relationship between the tip clearance of your blade and the overall duct hover lift augmentation efficiency factor. And so with a tip-driven solution, you can close off that tip leakage factor, and that has some pretty severe effects on the overall efficiency. So we'd have like a very quick comparison between a hub-driven open rotor with an MRAX 348 water-cooled or water glycol cooled. So that same MRAX 348 powering a ducted fan or a fenestron, and our maglev hyperdrive TX system, all the same diameter, I believe same tip speed as well. And so general just net difference. Looking at the CFD open fan, while easier to install, you're going to have all sorts of effects where the tips shed vortices that impinge on the following blade. This not only reduces the overall effectiveness of the blade, it also adds a fairly significant level of unsteady loading on that blade surface. And if you think about sound. It's the rate of change in pressure per unit time. Like a speaker, if you have something actuating a lot, it's going to be a very large source of noise. That unsteady loading can be 20 times louder than everything else in the rotor system producing noise. So it's a fairly tremendous source of noise for the overall system. The ducted fan systems can be better, where they can reduce a lot of these tip losses, but you'll still have some leakage, and you can see that here in the CFD, where the leakage, the shed vortices are still increasing the unsteady loading on the blades in the duct, and they also lead to earlier separation on the duct, which, you know, for a good ducted fan, you want it to diffuse so that you can have a larger low pressure region underneath that duct. So the better you can keep air attached to that surface, the more duct augmentation you can get from it, and the more thrust you can get for the limited area and power that you may have. So a tip-driven shrouded fan solution allows you to keep the air from leaking around the blades, which introduces less vorticity into that rotor, into the downstream of the fan, which promotes better flow adhesion to that duct surface. So you can, for the same duct geometry volume, you can have much higher duct augmentation factors. The net difference is, you know, fairly astounding, 62% more than open fan, roughly, you know, 20 or 15 to 18% more than the ducted fan. We also have some results showing pretty more dramatically improved, you know, cases as well. And then one thing to note as well is that there's no large blockage in the flow stream due to the motor in the inside. So we have a much smaller fan core, which helps us maintain flow adhesion to the sides of the ducts as well. So there's less dramatic change in duct area per unit distance down the duct. So the net effect is for a similar amount of weight, however, ours not needing to be water cooled allows us to reduce our weight slightly in comparison to the conventional systems. The same amount of power required, you can have a fairly tremendous amount of additional useful load. That's thrust, excess of the structure, the power systems, the weight of your devices, and the benefits can be fairly tremendous. So for 48% more thrust per unit power, you can have 230% more useful load. And that's, you know, however the airframer wants to be able to use that, whether or not it's payload, it's additional structures for, you know, harder landings or safety systems or fuel or endurance or range. However you want to use that is up to you, but it's more flexibility in the design space. So a few different ways you can imagine using these hover lift systems, very simple lifters, or you can put it into, you know, some more complex compound lift plus cruise kinds of vehicles, like a blended wing body, longer range, you know, slipper vehicle. And then this is a really cool opportunity, I believe, because, you know, we haven't seen many of these kinds of vehicles, and I think there's a good reason. But before we jump into that, I just want to say I'm excited about what is happening in commercial aviation with Jet Zero, Nautilus, and Airbus's zero-E efforts. This is an exciting time in general to see this happen. And the blended wing body, if you're not very familiar with it, has fairly tremendous improvements in overall efficiency, range, mass, structure, drag, fuel burn, all of these things for a bunch of different reasons, but the one that, you know, I think is the easiest to understand is where the mass is distributed in the vehicle. The aerodynamic loads also are similarly mated to and distributed similarly. So you don't transfer loads a very long distance in these vehicles. And so for an overall set of, you know, wetted area or, you know, wetted drag of the vehicle, you have the exact amount of wing that you need, and you have the smallest amount of additional structure that you need to be able to react against bending or shear loads on the vehicle. So it provides a pretty exciting opportunity in the vehicle design space to be able to improve the overall efficiency and reduce your fuel consumption, improve your speed, improve your lift to drag ratio, a bunch of very exciting things. So why haven't we seen VTOL blended wing body ducted fans? Ultimately, the things that high-speed, long-range blended wing body ducted fans they like them. You want to keep the minimal amount of excess wing area so that your cruise drag can be as small as possible and you can operate at your airfoil's highest lift to drag ratio. You want to keep the wetted frontal area to be as small as possible so that it has the lowest overall drag. And you want to have the largest internal volume for fuel, and in this case, liquid hydrogen, which is not the most volumetrically dense substance. But I guess batteries may not be that much better. But that being said, these things tend to disagree, or they don't comply as well with what you need for vertical lift. Vertical lift, you want the biggest area possible for your duct systems. These things, they want to be able to accelerate the largest volume of air, the smallest velocity delta into that system to decrease your power as much as possible. So you want to have as big of a fan as possible so that you can have the lowest power required as possible. And while you're doing that, you also, if it's a ducted system, you want to have the longest, deepest duct possible so you can diffuse that duct, the air, to an even larger volume as much as possible. And these things, unfortunately, coupled with the fact that you need power, not energy. Well, power is a much more constraining factor for vertical lift systems, which is very different than energy density or volumetric energy density that you need for cruise. And so these things don't agree with each other, and they make it fairly hard to close a design that is net better than what you might be able to do with adding some props onto a flying wing kind of a thing, and with an H frame kind of configuration. So it's not been worthwhile to try. Ultimately, if you can improve your hover lift efficiency, we believe that it could be worthwhile to try, and that's what I'm going to talk about here. So this is a vehicle concept we put together so that we could be able to share these results and have a discussion around it. Because oftentimes when we work with folks, those are their proprietary designs. So this is not necessarily a vehicle we're building right now, but it's a concept that we can show what our net impact is on a vehicle platform. Net difference is the targets being 1,000 pounds of payload, being able to have an internal volume of 3 A22 pallets, having a high lift to drag ratio, and leveraging stowable lift fans with our Maglev rim drive in a lift plus cruise blended wing body configuration with the objective to achieve fairly high range targets. Just to clarify, our propulsion unit consumes electricity. So it doesn't really matter where the power comes from. It could be battery electric, it can be hybrid electric, it can be hydrogen hybrid electric. Where the electrons come from don't matter, but we're going to talk about the liquid hydrogen in general as a use case here. So this is a great plot from the Uber Elevate back in the day, where Mark Moore showed where battery systems kind of lied on the specific power, specific energy. The higher up you are on the chart, the more energy per unit mass you can carry on board. And so the lighter weight your battery is going to be. The further to the left you are, or right you are on this chart, the more power you're able to deliver during fairly critical phases of flight, like vertical takeoff, climb, and then for dash opportunities. So ideally your high excuse me, you're high and to the right on this chart for the power systems involved, but it doesn't always tend to be that way. And so hydrogen power systems, they can have much better. Actually, this is a gaseous hydrogen with a carbon fiber wrapped tank, 5 to 10 kilopascals or kpsi, pounds per inch. The challenge with these systems is that for a specific fuel cell, which can have better, they have better power densities now. When you add redundancy into those fuel cell requirements, it severely impacts the overall specific power of that system, making it a little bit difficult to make VTOL by itself work. And so what we oftentimes do is we hybridize it. We add some buffer batteries to that platform, which then puts you on that slanted line purple here, where the more buffer batteries, the lower the overall specific energy, but also the higher your specific power can be as well. And you augment hybrid powertrains with some high specific power boost or buffer batteries to be able to fill in the gaps of your fuel cell. So if you can move yourself off of the conventional hover lift efficiency line and increase your power loading or your hover lift efficiency for a given disk loading or duct area, then what is the overall impact for such a vehicle with hybrid systems? So ultimately, the study that we're going to be sharing here is a slightly higher disk load than what you normally see in the eVTOL space. It's not as high as Lilium or some of the high disk load, very high disk load applications, but it is a little bit higher than your tilt rotor in that tilt wing disk load region. But even this improvement in hover lift efficiency has a pretty large overall impact. One thing to note as well is we've trained our models on, we've trained a lot of our tools and built surrogate models and seen where surrogate models tend to like to go, where they're given fairly abstract objectives and they show opportunities to even further improve the performance from where we are today in our simulations and our opportunities. So there's exciting opportunity ahead, we believe. So net difference is if you were to have that same MRAX 348 motor with tip-driven or hub-driven fan with your tip gaps, versus ours in this application is 287% additional payload, and that's from being able to, with the same power, be able to lift more, increasing the overall capacity of the vehicle. And so for the same range, you can carry more payload, or for the same payload, you could fly 200% further. Now, what's interesting is that becomes much more interesting when you're talking about liquid hydrogen, which instead of having a weight factor of 7%, meaning like the weight of the hydrogen in the tank and is like 7% or versus the overall tank plus fuel cell, the weight of the hydrogen now in the tank can be, much more significant in comparison to its enclosure, around 25%. And the difference can be additionally, 270% more payload or 200% more range, but now you're talking about pretty compelling range capabilities for such a slippery high lift to drag ratio vehicle. Reaching from 1,000 to 2,000 nautical miles. Now, of course, we did a really coarse mission study. I think the term is zero credit approach, but generally speaking, we're pretty excited about the implications that such propulsion paired with advanced airframes and vehicle systems that are available to us through the advancements in controls and in design tools, et cetera. So high level, better hover lift efficiency can have pretty outsized effects in payload. And, as for the vehicle designers in this, in this room, we've all experienced this more in the latter, where something is not as efficient as we think it is, and therefore the consequence is quite painful. But when things are more efficient, the implications can also be quite impressive. This is just like a slide saying that you don't always have to carry it as all cargo. You can, instead of having 3 cargo pallets, you can replace it with 1, 2, or 3 liquid hydrogen pallets. And with all of it being hydrogen, just a big old flying bottle of hydrogen, could have pretty extraordinary range and endurance with such a system. We're working with a few partners in the Air Force and in DARPA, and we're always open to more partnering opportunities to understand how we can better help and enable new outsized capabilities. This is more or less what I got. Thank you, guys. And we're starting with cargo in defense applications, and we think they can transition to cargo and commercial applications. And then, of course, we'd like to get to passenger vehicles, but it's going to be a minute before we do that. Thank you, guys. That's what I got. So love to have a discussion if possible, or whatever the next steps would be for the discussion here.
All right. Thank you so much, Ian. I mean, every time I listen to you, your talk, feel like drinking from a fire hydrant.
I apologize.
That's a packed information, and many of the points that you point, I can absolutely relate to. Been working on Dr. Fan and stuff like that, so truly appreciate this information-packed presentation. So open to the floor, guys. Yeah, let's ask some tough questions.
Please, please.
While folks are thinking about their tough questions, I do have one for you. Now, it looks like the aerodynamic enhancement that's pretty much for us aerodynamics. It's a dream come true. Virtually, you have no tip loss, and all the complex problems, and the ability to maintain tight gap on the ducted fan, that has been central challenges. So we solved some of the problems with a lot of penalties,
Yes.
structure, weight, complexity, and cost, and so on. Now, but the way that you were able to devise your the outer ring driving ductless propulsion system, the net equivalent, say, same lift that you're able to. Is the system that you were able to demonstrate in the same weight category as the conventional ducted fan, or larger open rotor?
Yeah.
How's the weight and complexity comparison in your mind?
The weight is fairly similar. The net system weight is fairly similar. The complexity, we have an improvement, and also the net system weight is similar because of a few motivations. Like oftentimes in these lifting applications, not only do you need to be able to produce thrust, you need to be able to produce thrust with a relatively high bandwidth for attitude control of these vehicles. So being able to increase and decrease your thrust around a certain target. So we add a little bit more muscle into the system to be able to boost up the rotor speed to allow for a relatively simple overall rotor system. So no complex pitch control linkages or stuff like that in our first application. And we design around air cooling specifically as an objective for those lift fans, so that you don't need to augment that base installation with additional water cooling or oil cooling, radiators, pumps, measurement systems, and fault mitigation methods as well, with what happens when that leaks or is clogged for some reason. So net complexity, as the the airframe, they deliver to the propulsion unit a command signal for more or less thrust. It delivers that thrust. The complexity coming out of that, yes, our motor is going to have a lot of insight into the dynamics happening inside of that rotor. You can either choose to use that or not, but it's not necessary to put in there.
For the one that you were, showing the potential use case, like the study you shown the 1,000-pound payload
Yeah.
vehicle, are you rely on blade pitch variation to change the lift for controls and so on, or do you rely on the RPM control as a primary changing mechanism?
We have two versions, one with RPM control and one with blade pitch control. They're quite literally actually in the renders that are in that presentation that I just gave. That was actually the one with the pitch control unit, a multi-fault tolerant redundant pitch control. So changing collective pitch, not individual blade pitch control.
Okay.
Yep.
And the main choice is it's a fast response time or
fast.
All right.
Fast and being able to create net positive and net negative thrust.
Got you. Hey, Evan.
Yes, this is Ivan Clark and Nessa Langley.
Yep.
Thank you for the presentation, Ian. With the rim driven, I would expect that the blade mass is shifted away from the center and towards the rim in terms of the strength of the blades. What happens to the gyroscopic moment of these motors when you're doing maneuvering or when you encounter turbulence?
So it's a good question. I mean, that is part of the main reason why we add maglev stabilization at the rim. Just as a standard motor, you can react a lot of those loads through the stator at the center, but it's a really long distance that those loads get carried through the blade, which is why we add some stabilization. It has some natural stiffness that comes from just it running at speed. So
yes,
there are
but
those
I'm asking about the gyroscopic moment effect on the vehicle.
Oh, on the vehicle.
That it has an ultra stable platform, and you won't. The good thing, so sounds to me, is that you're probably immune to the gust behavior lesser. But if you want to turn it, you may not want to turn, huh?
Yeah. No, it's a good question. It's not going to be like a very, very stable rotor like a helicopter with very, very large moment of inertia. I don't think it's so much more severe from a perspective of the overall moments of inertia in comparison to a ducted fan, maybe a few times larger than a conventional ducted fan. But it is a good question. In our dynamics models, we do have those moments in the model, but I haven't seen an analysis that we've done to see what the overall net impact of the moment of inertia is on the vehicle. So that's a interesting thing I want to understand myself.
Yeah, and for our, years ago in our turbulence work, we actually encountered on a 757 plus and minus 2 Gs over a 5-second time interval.
Oh, wow.
That was when flying close to a thunderstorm.
And that it was just produced from the ducted fan.
No, that was from encountering turbulence, atmospheric turbulence on a fixed wing 757.
Yep.
If people weren't belted, they would have hit the ceiling hard.
Jesus.
So that's the sort of thing that once you get to commercial flight, you can actually expect to encounter.
Oh yeah, no, we do design towards fairly high G maneuvering loads though.
Okay, thank you.
Great question.
Can you talk a little bit about your fuel cells? So, one of the issues we've looked at, we've looked at hydrogen fuel cells and so forth, but just getting fuel cells with enough power capability to power, during the VTOL phase of flight. Have you been able to find suppliers that can do that kind of high power fuel cell stuff?
No, the assumption here was the impact on the vehicle was that it reduces the buffer battery required to augment the additional power requirements. We're not assuming high temperature fuel cells or anything really sporty like you may be, kind of hinting at there. We were assuming regular low temp PEM fuel cells with a I want to say 10C buffer battery. So something a bit sporty on the battery side, but not out of the realm of reasonable when you have a battery specifically designed to sacrifice a bit on energy density for the sake of power density.
Yeah, thank you. That makes sense. That's a good strategy. Just kind of trickle charge the buffer battery with the fuel cell
Yep.
at a more leisurely rate. And then for cruise, I might have missed this part, but for cruise, were you talking about also having electric rotors for cruise, or are you thinking more of a conventional fuel?
That one is totally up to the airframer. I think the analysis we did was electric fans. So the powertrain was power gen through battery and fuel cell. So the fuel cell powered electric fans for cruise. I think we assumed 80% efficiency for the cruise fans there. But there's certainly a lot of credibility and a lot of opportunity around parallel hybrid configurations where you won't have the transmission losses from power generation for your higher energy density power generation, like a fuel cell or a hybrid turbo fan or a turbo genset, where you can deliver that power mechanically to a cruise fan for the duration of your go period, and then augment power with an electric system for climb, boost, whatever, dash, whatever you may need.
Okay, thank you. Awesome.
Andy, you have your hand up.
I do. Ian, excellent presentation as always. I was going to ask your thoughts and projections on scaling down in terms of physical size. When we think about applying your technology to a UAV or applying to a standard scale aircraft, but just using a lot of propulsors, what are your thoughts about how scaling can work?
That's a great question. One that we spent so much time figuring out how big we can go that we haven't spent as much time on the how small we can go. But there are a few challenges with going smaller, actually. And it does come down to be more of a thermal, it's more of a thermal set of challenges. So when I show this, we don't have plans to build one this small. Actually, the first one that we're building and working on with people and some airframers is about 4 times this size. I think there are opportunities for a little bit smaller, but how much smaller? I'd wish I had a number. I apologize.
That makes sense. It gets expensive. Everything to miniaturize anything gets expensive. It's better to start with standard size and get good at that.
Yep. Eric.
You might be on mute, Eric.
Yep, sorry about that. Hey, this has been incredible. Thank you, Ian. The question I have is more so for professional connectivity and getting you connected with people you need. Is there a gap currently, based on something you said earlier? It sounded like as far as partners that can build certain things, are you finding the right people in the US to be able to build some of these specific high-tech things? Are you building them in-house? Can you talk about that or share more?
Yeah, no, we leverage our third-party manufacturers and supply chain partners quite heavily. Some things we can build in-house, but some things we have to go out of house to procure or produce. And so having a healthy Rolodex of supply chain partners is a really important component in the overall, endeavor. So that being said, if you want to connect me, I'd love to have follow up and have a discussion about, where some of the openings. Definitely one discussion about where you get magnets from. It's always good to have more sources for those. And controllers, inverters, blue chip technologies, composite manufacturing partners, all of those things are, we can always have better power electronics partners. Yeah, the whole network, I could say, is always something that we're looking to improve.
Great, thank you.
Oh, Ken. Oh, you're muted if you're talking, Ken. Uh-oh, it may be my share.
No, Kent, we can hear you okay, but we cannot hear Ken.
Hi there. Can you hear me now?
Yes, we got you
Okay.
loud and clear.
Okay, sorry, there was just working on the handheld app version of program. I appreciate the presentation today and also the one you gave at TVF about 3 weeks ago.
Mhm.
Just want to clarify something because you talked about maglev for stabilization, but the impression I got is that the drive system is actually in the rim as well.
That's
And is
right.
that okay? So what you're saying is that it's both providing the forward momentum or the drive, but secondarily, it is providing the stabilization of the outer ends of the rotor or the blades as well.
That is exactly right. That's
Okay.
exactly right.
Okay, because I did write up a report based on what my understandings were when I heard you at TVF, and then I thought, well, if you're just talking about stabilization, so what you're saying is then it plays two roles.
Yep.
Then,
You
okay.
put a lot of muscle out there. We use some of that muscle to also stabilize the rotor. And then also the standard machine, the machine type that we use, introduces less inherent instabilities as well.
Okay, thank you very much. Thanks for the clarification.
Yep.
Hey, just one quick question, follow up on that one. With the drive on the outer rim, seems to me that give you a lot of control compared to a centralized motor drive. Is that the case?
You do tend to get more torque density as your diameter increases. The only reason why so hypothetically, if all things were perfect, which unfortunately they never do tend to be perfect, as your diameter increases for the same overall height of a motor, your torque per unit mass should increase linearly. Now, the reason why it doesn't in the real world is because as your diameter gets larger, for the stiffness of the materials involved, your deflections get larger as well. And so the way that electric motor designers mitigate against that is they increase the air gap. Now, air gap is the most critical design component that we have as motor designers to play with. And it's the thing that we're always trying to make smaller. And as you get bigger, it's always trying to get bigger. And so there's scaling factors associated with that. So normally torque density does this kind of a thing. So with ours, we do see fairly large torque densities because we can enable a smaller air gap for a relatively large diameter system.
So in a way, we're trading the aerodynamic gap problem to the motor gap. So am I correct? There's maybe a sweet spot?
There is, and it's really interesting where it is.
Okay. All right. Well, we're approaching the end of our session, and this is fantastic session. I really enjoyed it very much myself, and I'm sure everybody else is. And I'm sure we probably, after we think through a few hours, so we'll probably have more questions, ideas, or So everybody, if you need to get hold of Ian, I think many of you know Ian already. Please do so, and if not, let me know. I'll make sure that you get in touch with Ian, with this fantastic, interesting, innovative approach on solving a century-old problem. So I'm really encouraged.
I just dropped my email in the chat here. If you guys please reach out, connect with us. We love being able to connect with this fantastic industry of folks and get better and do more impressive things. So that's what we want to do.
Okay. Sounds perfect. Thank you so much, and thank you, everyone. I'll see you guys next time.
Thanks, everybody.
Thank you.
Thank you.
Very much.
Excellent job.
Thank you.
Thank you very much.